Yay!
Yay! Let's do one more two-dimensional conservation of momentum example. This time, let's do something a little bit different, and let's do a completely inelastic collision. So I have one, maybe these are lumps of putty that stick together, or if the masses were different, maybe these are cars that stick together after a collision, right? Something like that. So anyway, suppose I've got a 2 kilogram mass that travels sort of southeast at 6 meters per second, and it hits a northbound 4 kilogram mass at 4 meters per second. And suppose they stick together. So this is stick together, and we said that was completely inelastic. What I want to know is what the final speed and direction of the sort of the wreckage is afterwards. All right, so what we do, again, it's always the same thing. We do the initial momentum is the final momentum, and these are vectors. All right, so what's the initial momentum? Well, I got two pieces. There's one mass's momentum and the other mass's momentum. So let's write it down. So PI has got a couple pieces. The mass is 2 and 6 meters per second. And at 6 meters per second, suppose this is like a 45-degree angle. Maybe it's, southeast. So that's going to be 2 times 6 cosine 45. There's the x component. And then the y component is going to be 2 times, it's going to be negative, isn't it? Because it's going sort of down and to the right. So minus 2 times 6 sine 45. Okay, that's one mass. And now I got to do the other one. This is going to be, it's not doing anything in the x. It's going to be 0. And then in the y direction, it's going to be 4 times 4 meters per second. Oh, well, that's going to be easy. That's going to be 16. Right. And then this is going to be the final momentum. This is going to be the two masses stuck together. And so their combined mass is going to be, looks like 6. And I don't know what Vx and Vy are yet. So let's just leave them as variables. Vx, 6 Vy. Okay, so there's the conservation of momentum. There's the principle written down. And so now all we have to do is just solve for Vx and Vy. All right, 2 times 6 cosine 45. What is that? Let's see, I did it already. That's going to be 8.48. Leaving off the units. And let's see, on the bottom I get minus 8.48. Oh, and it's 8.48 plus minus 8.48 plus 16. And when I do that, it looks like I get 7.51. There we go. So those are those two vectors added together. So this equals 6Vx, 6Vy. So now to solve for Vx and Vy, well, that's easy. Now I'm just going to divide by 6, right? Both equations divide by 6. So this turns out to be pretty easy. So my velocity vector, which is Vx, Vy, is just going to be 8.48 divided by 6 and 7.51 divided by 6, and that is 1.41 and 1.25. There we go. There's my velocity vector. If you're asked for the magnitude of the velocity and the direction, then you could say, let's see, that's the square root of 1.41 squared plus 1.25 squared, and I did it already. That's 1.89. I'll stick the units in at the end, 1.89 meters per second. And then the direction is just going to be the inverse tangent of y over x, right? And so if I do that, inverse tangent of 1.25 divided by 1.41 gives me 41.6 degrees. Okay, so the final thing, is going to be going off in this direction. So 41, it's going to have a mass of 6, and it's going to be going in a theta of 41.6 afterwards. And so if you draw it out, well, that kind of makes sense. If those two things collide, then that's going to be the direction that the sort of the combined object heads. And so again, this is how you do conservation of momentum in 2 dimensions, is you just do it as vectors. You just sum the vectors together and then solve for what you don't know. Very cool.